Hi everyone, welcome to Design and Application of Lasers. I'm your instructor, Dr. TJ Hammond. This is for the lecture of Wednesday, September 23rd. So, we're going to continue on this lecture on absorption, emission, and dispersion of light. And why are we covering on this? Well, last week, as I said, we discovered, discussed that atoms have these discrete energy levels, these states, and molecules also have these states, but these transitions are more in the infrared. And we also have solids, which also have these discrete states, but they end up forming, so many atoms are formed together in a solid, and so these discrete states become bands. But now what we want to discuss is how we can actually excite these atomic or molecular or solid transitions. And so we want to understand how light can interact with these electrons, or how light can interact with matter. How does this light get absorbed, and what happens if this light doesn't get absorbed as it propagates through this material? So the daily assignment for Friday is read and summarize section 3.4 on absorption. Hopefully we'll be getting to that today in lecture, but if not, if you read it, then on Friday we'll be able to quickly get through that material, and then it won't take us so long to cover it, and so that we can cover more things on Friday. It'll also be relevant to your assignment this week. Okay, so from Monday, we had this electron oscillator model. We had an electromagnetic wave that's propagating here on the left. It's traveling in the Z direction. It's polarized in the X direction. The magnetic field is polarized in the Y direction. As we said, an electromagnetic wave is polarized based on the electric field, and in free space, the field polarization is orthogonal to the direction of propagation, so propagation in Z, polarized in X. And then in Y, we have the magnetic field, and this has to be polarized both orthogonally to the electric field and to the direction of propagation. So that's why this wave looks like this. Now this electromagnetic wave hits some atom here, and we're going to model this atom as an electron that's very light, and that is attached to this nucleus, which is very heavy, by some spring. We have no idea what this spring is, but it's just some kind of magical spring that allows the electron to oscillate kind of about this fixed state, this fixed distance from the nucleus. So we put this model into a differential equation. This ended up being the exact same equation as a driven damped harmonic oscillator. And so we just got the exact same differential equation. And then what we said is we want to solve for the steady state. And so the steady state being this amplitude of this electron. So what we found was that the steady state value that we got was complex. The amplitude of this steady state, the amplitude of this electron oscillation ends up being proportional to the electric field. So how strong we're driving this process, that's going to tell us the amplitude of this electron, of this motion. It's also proportional to the electric charge, but that electric charge basically tells us how strongly this electron can couple to the field, so that also makes sense. And it's inversely proportional to the mass. But that makes sense because the electron is very, very light, and so an electron is about 2,000 times lighter than a proton, and this nucleus can be made up of many protons and neutrons. And so even for a hydrogen atom, this electron moves about 2,000 times more than the nucleus, but for something that's much heavier, such as xenon, this nucleus is hundreds of thousands of times heavier than an electron, and so this nucleus we're just going to assume is stationary while this electron bops up and down as caused by the electric field. So, but we found that this thing is complex, and we found that the reason why this is complex is because in the denominator here we have this gamma. This was the damping parameter, if you remember. So we have in the denominator we have, if we don't have this damping parameter, then what we have is omega naught squared minus omega squared. So what that's telling us is how close we are to this natural frequency. So omega naught squared is k, our spring constant, divided by m, the mass of the electron. And so that's, of course, this natural frequency of this electron on the spring. And however close we are with our oscillating electric field, if it's really close, then this amplitude gets really, really big, and this electron oscillates with really large amplitude, and if we're far away, then this doesn't oscillate very large at all. But then we also have this damping parameter, and this damping parameter is multiplied by I, the complex value. And so this ends up being that this response, this amplitude of this electron, is actually going to be some complex value. And so so what we need to do then is, of course, if you've dealt with complex numbers before, is multiply this denominator by this complex conjugate. And so what we get out are two terms. So we'll be dealing with x of t, so what the position is as a function of time. And this first term, what we get is something that oscillates as e to the minus I omega t. So remember, we're driving this thing with a field at e to the minus I omega t. But then we also get the second term, which is I times e to the minus I omega t. And if you remember, I is actually e to the I pi by 2. And so what we get are two terms here. So this x of t, as it's oscillating as a function of time, has a part that oscillates in phase. So that's in phase to the driving field, which is e to the minus I omega t. So this thing oscillates with the same phase as this field. But then there's also a complex part, or sorry, this right-hand term ends up having this e to the I pi by 2, and that causes this thing to oscillate pi by 2 out of phase. Okay, so it's not completely out of phase. It's not when this electric field is up, the electron is oscillating completely out of phase. It's pi by 2 out of phase, so when the electric field is at a maximum, the electron's at 0, and when it's at a minimum, the electron's again at 0. So we have a term that's in phase, and we have a term that's what's called in quadrature, or pi by 2 out of phase. So what does that mean about how this light is going to interact with this material? And that's what takes us to absorption and dispersion. So you should have learned by now about the polarizability of a material. If you've taken electromagnetic theory last year, you've definitely learned about this, and I talked about this in electromagnetic waves. For those of you who are taking electromagnetic theory now, Dr. Rao should have reached this material by now, or maybe in the next few lectures, although you probably should have seen something like this in EM fields and photons as well. This is the basics of what happens when you apply an electric field to matter. So if you have some neutral object here, we have this purple blob, and it's made up of positive and negative charges. And then we apply an electric field to this thing. So this electric field is, of course, proportional to a force. And so this is forcing these positive charges up, and it's attracting negative forces down. And so this blob gets separated into a mass of positive charges and a mass of negative charges. And these two things get separated. And so there's still obviously overlap because this thing isn't completely separated. But you end up with the center of mass of the positive charges is up here, and the center of mass of the negative charges are down here. And you get this separation distance here, and we'll call that separation distance x. And so the polarizability of this material is the measurement of these charges being separated by a distance x. And that is what the polarizability of a material is. Now, what we'll be dealing with here is the linear case, which is that the polarizability of this material is proportional to the electric field that we apply. So that means that if we apply this electric field like this gives us some certain separation of these two charges. But if we say double this electric field, then that means that the separation of these two charges would just double as well. Later on, towards the end of this course, when we talk about nonlinear optics, we'll be talking about what happens when you have a nonlinear response to that electric field. But in this case, we're just going to say we have a linear response to this electric field. Now, if you have a linear response to this electric field, well, that means that this polarizability of this material is proportional to the electric field, and we can give that constant of proportionality just some number, and we'll call that chi. And we also stick in here the epsilon naught, the permittivity of free space. So why we care about this is because we have this oscillating electromagnetic wave. And so the general form of a oscillating electromagnetic wave in free space is given here on this left-hand side, where we get a second order differential equation in space of the electric field minus mu naught epsilon naught, so the permittivity of permeability of free space times the permittivity of free space, times the second derivative of the electric field with respect to time. But the permittivity times the permeability of free space is 1 over c squared. And so that gives us that this is the velocity of this wave is going to be traveling at the speed c. And that would be in free space, this would just be 0. But we're not in free space. What we actually have is this electromagnetic wave that's oscillating in space and in time, and it's now hitting some matter, okay? And this matter is made up of these charges, okay? And that's what's going to be moving around. So this generalized form is that we have this mu naught and then the rate of change of this current, okay? Now, the current is going to be some charge times some velocity, and so the rate of change of this current is going to be giving us the second derivative of this rate of change of this polarizability of this material, because this polarizability of this material is some charge times some distance. And so what that means is that instead of this being so that means that this is now the second order derivative of this position, because we already have that the current is the first order derivative of the position, and so we take the derivative of that, so we get the second order derivative of that. And so what that means is that we get, on the right hand side, we get epsilon naught chi, and then the second order derivative of the electric field with respect to time. But that's what we already have here. We have this mu naught epsilon naught here. Oh, this is missing a mu naught here. And so what this means is that we have these constants go in front, and we can bring this over to the left-hand side, and what we get is the second order derivative of the electric field with respect to space minus this modified mu naught epsilon times the second derivative of the electric field with respect to time gives us 0. And so this is a form of a wave. This is the wave equation, right? Where the speed is given by 1 over the speed squared is given by this epsilon mu naught. But the thing is that we have this response of this electron to this electromagnetic wave is actually some complex value. We have a real part that's oscillating in phase, and we have the second term that's oscillating pi/2 out of phase, and so this is complex. And so what we say is, instead of this just responding proportionately to this electromagnetic wave, we have this x is going to be some complex value. So what we're going to say is that this thing here is going to be some complex value, and so our electromagnetic wave is then some complex value. So we can rearrange this to write it like this. It doesn't really matter what the exact form is. Basically, it's that this constant of proportionality is going to be complex. And so if you think about what this means to the electromagnetic wave as it propagates through this material, what we have is the wave propagates at speed c, is going to be instead, in free space, it's going to be instead propagating as e to the I kz minus omega t. But kz minus omega t, these are related through these constants of proportionality. And so it turns out that if we do some math, and we'll be doing this math in electromagnetic waves, but for those of you who haven't taken the course with me yet, just trust my word on it, just take my word for it, that we can separate this k into a real part and an imaginary part. And so basically what we have is this complex response to this electric field, to this applied electric field, gives us a complex wave vector as this wave propagates in the material. And so we get this complex wave vector, and we stick that into this k value here. But since we have an e to the I kz, then what we get is e to the minus k, the imaginary part, z, which is a decaying exponential, and then we have e to the I krz minus omega t. So this part still oscillates like a cosine function, but it decays in magnitude. Okay? So So what that means is that this plane wave, this electromagnetic wave, as it's propagating in free space, it now hits this material, and if this material has a complex response to this applied field, then that decays or that attenuates the amplitude of this electric field. But if it doesn't, then, well, there's also going to be a real part, and that's going to be changing the phase of this wave as it propagates in this material. So what that means is we can write this a little bit more sophisticated, but we can write that the square, or the square of the index of refraction is given by this term here. So it's 1 plus some constants up front, but then we have this omega squared j, that is the jth resonance. So I'll go back to here. We had this omega naught squared minus omega squared. This was for one particular resonance of this electron, but this electron can actually turn out to have multiple resonances as it has multiple states, and we'll get to that soon. But we have this equation here is effectively the first term in our equation here. And so this thing that oscillates in phase will determine the index of refraction of our material. And this part that is oscillating, let's say here, this part that's oscillating pi by 2 out of phase, you can see that you get this gamma omega over this denominator. That is the part that is going to be here. We have this gamma here. And this is going to be the part that's oscillating pi by 2 out of phase, and this is called the absorption coefficient. Okay, so basically what it is that we've done this calculation for this electron that's oscillating in this electromagnetic wave, and it's causing this electron to change its amplitude, and there's a part that drives in phase, and there's a part that drives pi by 2 out of phase, and the part that drives this in phase is going to be changing what the index of refraction of this material, whereas the part that oscillates pi by 2 out of phase here is going to actually lead to absorption of this radiation. I guess I will stop here for now, and maybe we'll get to this in the lecture, but if not, we'll be talking about this on Friday.